AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, good morning, good afternoon, good evening, friends of AI, Earth and Sustainability. First, I would like to welcome you, everyone, to this new talk in the seminar series of AI for Earth and Sustainability Science. This seminar series in the program AI for Good of the ITU is co-convened by myself, by Michael Reichstein, Joachim Densler, and Maria Piles, and was actually initiated some years ago in the context of the Excellence Network ALICE for the development of AI in Europe. First of all, thanks for attending this meeting, all of you. Today we will hear about fast statistical inference with neural networks and amortization, with special emphasis on applications of spatial environmental and geophysical applications. It's my absolute pleasure to present our speaker today, Andrew Samit-Magnan. Andrew is an associate professor at the School of Mathematics and Applied Statistics at the University of Wollongong in Australia, and his interests basically revolve around spatial temporal models and inference tools for environmental applications. He has published extensively in this field of dynamical spatial temporal modeling, Bayesian hierarchical modeling, and approximate Bayesian inference. And he's very active and very nicely active in releasing software packages for that. He has been recipient of many different important awards from the American Statistical Association, from the Bayesian Analysis International Society, and the National Academy of Science in the US. And today's talk, we will see interesting takes, I think, on neural network amortization for geospatial data problems. I hope we can learn actually if amortization is the key to our goals or it is just a dead end and a red herring, as Martin has put in the title. So welcome and thank you for being with us today, Andrew, and over to you. Really looking forward to your talk.
Thanks a lot, Gustavo, and thank you everybody for coming. I'll just share my screen now. Okay. So let me just hide the controls. Okay. All right, there we go. So thanks everybody for coming. So my name is Andrew Samit-Magnan. Thank you, Gustavo, for the introduction. Today I'll be talking about fast statistical inference with neural networks and amortization. So there's quite a lot in that title, and I'll slowly tear it apart in this talk. I'm from the University of Wollongong, and I'm sure not many people know where Wollongong is. So I thought in my first slide I'll quench that thirst and show you where Wollongong is on the map. So it's in Australia, and Sydney is just 1 hour north of Wollongong. Wollongong is a seaside city. It's pretty big, I'd say medium-sized university. And yeah, if anybody is down in Sydney for a holiday or for work and wants to visit, it's always a pleasure to welcome visitors. All right, so this is joint work with Matthew Sainsbury-Dale, who is my PhD student who submitted, and Raphael Houser from KAUST in Saudi Arabia. All right, so a bit of a background, what I do. So I've been working on spatial and spatiotemporal modeling for the better part of maybe 15 years now. And essentially what this is you get some data set which is spatial or spatiotemporal, and you either need to fit a model to that to estimate some parameters in there, and those parameters could be interpretable, they could mean something important, or you want to forecast, or you want to do both. So this has applications in conflict prediction, for example. That's something I worked on about 12 years ago. Sea level rise prediction. A recent project I've been working on with NASA is on predicting carbon dioxide sinks and sources, and estimating the fluxes from satellite data. So all these problems involve big spatial or spatiotemporal data sets, which require some form of analysis, and in my case, some form of statistical analysis. So this webinar series is AI for Good. So I thought of not just talking about spatial statistics, but also how neural networks are affecting our field. So when you just look at the number of publications which contain spatial statistics and deep learning, 10 years ago there was virtually nothing, maybe a few papers here and there, but now we're counting 1,000 per year. And this reflects, of course, the recent growth in AI. So if we just look at how many publications contain the expression graph neural network, again, it's very, very few comparatively 10 years ago compared to what we have now. And I'm choosing graph neural network because I'll talk more about graph neural networks later in the talk. So of course, AI is affecting many fields, and statistics is of course one of them. All right, so how do we use neural networks in spatial statistics? So as I said, many times we want to model a process so we can predict at unobserved locations, for example. Just think of, for example, temperature. I've got some monitoring stations and I want to predict the temperature where I don't have a monitoring station. Neural networks can give us the capacity to model very flexible spatial processes, and that's what we've been doing recently. So that's spatial process modeling. Another place where neural networks can really make a difference is in emulation. So this is the case where you've got say a very complicated physics model, for example, that you need to simulate forward many times for various reasons, and this physics model could take a long time to run. Okay? So maybe it has finite elements, solvers, and things like that. So what we want to do many times is make a surrogate model which we can replace the full physics model. And neural networks are very good at learning these complex mappings between the input to your simulator and the output. Okay, so we've been using that a bit as well. And the next thing is parameter inference, and this is what I'll be talking about today. So the idea here is we want to train neural networks to make amortized parameter inference. And I'll talk about amortized quite a bit, but in summary, there are various ways in which you can do amortized inference. And today I'll be talking about possibly the simplest way, which is called amortized point estimation. So point estimation, what it means is that I want to just give you a best guess of a parameter. Okay, I'm not giving you a distribution, I'm giving you a best guess. The other methods will actually give you posterior distributions over the parameters. The word amortize means that I get these parameter estimates using a quick forward evaluation, in this case via a neural network. So what is amortization? So an official definition which I found on Oxford Languages is the following. It's the action or process of gradually writing off the initial cost of an asset. So in our case, in the context of neural networks, This initial cost is that of training the neural network. So in order to develop this neural network that gives us a parameter estimate from data, we're going to have to train that, and that requires, as I'll show you later, a lot of simulations. And of course, then you need to do the training on GPUs or on expensive hardware. So there's a big initial cost. But if you are going to repeatedly use that neural network for the same inferential task, then you're going to reap dividends, okay? That initial cost is justified. So this is what we mean by amortized inference. This is a visual which summarizes what I just said. So what I've plotted here is a happy statistician with a client, and the client is asking the statistician, can you fit this model to these data by the end of next week? And the statistician is smiling. She has many tools at her disposal, from STAN, maximum likelihood estimation, and things like that. But now imagine the client says, can you fit this model 100,000 times a day, every day for the next 7 years, because data's coming in all the time and we need to fit this model. And of course now this is not, it's a totally different ball game, and the statistician looks a bit worried. So amortized inference really comes into its own in these situations where you have to do inference many times, for potentially 100,000 times a day. Now, which sort of client will demand you to do this sort of level of computation? And these clients, satellites, tend to be very demanding. So what I've got a picture of here on the left is orbiting Carbon Observatory 2. It is a NASA satellite. And this satellite was put into space about 10 years ago now, so that we get more information on how much carbon dioxide there is in the atmosphere. Now, of course, there's no carbon dioxide in space. So the way these satellites work is they actually look at the intensity of reflected light from the Earth's surface. And depending on what the how the intensity is as a function of wavelength or frequency, that tells us something about the constituent gases in the atmosphere of Earth. So if there's a lot of carbon dioxide, for example, certain wavelengths will be more absorbed. The power associated with those wavelengths will be less. So in this case, we observe Z. I'll be using Z to denote data. Okay, so Z is data. But really we want to infer what the carbon dioxide is in the atmosphere, and I'm going to denote that as theta. This is the unknown we are interested in. And how are the two related? Well, there is what we call a forward physics model, which I'm denoting as H, which relates theta to Z. Okay, and generally speaking, it's quite easy, to easy in inverted commas, to go from theta to Z. But actually we want to do the opposite, right? We observe Z, which are these intensities, and we want to go backwards to theta. So this is known as the inverse problem. And there are some uncertainties, that's why I put epsilon in there. So solving this inverse problem is actually quite complicated. As I said, the satellite does 100,000 soundings per day, or even more actually. And all of these, so that's 100,000 inverse problems that you need to solve per day, okay? So currently that takes a lot of time, and what we're seeing coming up, and there's this nice paper over here, is neural networks can be used to go from Z straight to the unknowns, okay? And I'll be talking about how we can do that later. All right, this is another example. So forecasting sea surface temperatures. So again, it's the same sort of system. So we've got Z, and Z is the recent history of sea surface temperature, and we want to learn theta. So theta in this case would be parameters in some partial differential equation which governs how sea surface temperature is evolving over space and time. So in this case, it's a simple advection diffusion type equation, where these parameters actually are changing in space and time. So why would we want to infer these parameters? It's a classic forecasting problem. If we know what the parameters governing the partial differential equation are, then it's relatively easy to predict what's going to happen at the next time step, which could typically be 1 day. So what people have done is they take the recent history of sea surface temperature, which you can cast into a kind of a 3-dimensional array, space 2 dimensions and time 1 dimension, and you can put that into a neural network, for example, a convolutional neural network. And you train this neural network so that it actually spouts out the parameters of this partial differential equation. And once you have those parameters, then you can put that into your solver to get your next time point. Okay? And if you want to do this at a local scale over the whole world every day, again, this is a process you need to be doing very quickly with minimal computation. So this is another place where amortized inference is really useful. Okay, so you want a neural network where you just give it Z and it will give you theta straight away. This is another example. This is the final example I'll be giving before I go into some more detail into how these things work. So this is now modeling extrema, so sea surface temperature extremes. So there are some statistical models, we call them spatial models of extremes. Very difficult to make inference with. They have what we call an intractable likelihood. So they've got an intractable normalizing constant, which makes the likelihood intractable. So making inference with these models is very difficult, but they're very useful to have because they can tell us things like if there's an extreme sea surface temperature event, this is the Red Sea, for example, what is the spatial extent of this extreme? Is it very localized, or is it, for example, does it have a lot of spatial correlation? So this is why we would want to fit these models. And in the case of the Red Sea, there's a lot of coral. I went snorkeling there a couple of years ago. It's really beautiful, but there's also a lot of coral bleaching because of the sea surface temperature, of course, which is going up, like in most places. So again, we can simulate these spatial extreme from these extreme spatial process models quite easily if you give me parameters theta. But going the other way from the data to the parameters of interest is very difficult. Okay, so this is again another place where amortized estimators can be very useful. And there are countless other applications where actually having this functionality would be very useful. Okay, so this work is discussed more in this paper, which is published in the American Statistician. All right, so I'll be talking about some ideas which do appear in the paper, but what I'm going to do now is actually delve a bit into the maths, because one question which obviously comes up when you're using neural networks to do these things is, how do you know it's giving you the right thing? Can we trust it? Okay, is it reliable? Is it robust? And to really start answering these questions, we must have a bit of an understanding as to what's going on underneath the hood. And then after I discuss a bit of the maths, I'll give you an application, then discuss some practical things to do with amortized inference, and then we'll conclude with, is it a golden ticket or a red herring? Okay, then we'll go back to the title. All right, so there are two key ingredients for amortized point estimation in a Bayesian setting, which we need to first establish. The first one is Bayes' rule. Okay, so the Bayes' rule is as follows. P of theta given z, we call this our posterior distribution over our parameters theta. So you can think of this as our best beliefs on theta after we have observed the data z. And Bayes' rule tells us that we can express this as following. It's the likelihood function of theta. So what is the probability of observing this data z given theta, multiplied by our prior beliefs on theta, so that's before we have observed the data, divided by what we call the marginal distribution of the data. Okay, so what is the distribution of the data without any information about the parameters? So we will be using this quite a lot because it links our best beliefs on theta after we observe data with whatever we have before. The second thing is the loss function. So the loss function quantifies the cost with getting with our estimate being wrong. Okay, so we have L of theta comma theta hat. This function here tells us what is the cost of theta hat not being equal to theta. So for example, if the true parameter of interest theta is 0 and our guess theta hat, our estimate is 1, we could have a squared error loss, for example. That means that our loss is 1. Okay? It's 1 minus 0 all squared, which is 1. So it's as simple as that. Using these two ideas, we can come up with what is called a Bayes estimator. Okay, so a Bayes estimator is as following. I'll talk actually about estimates first, and then I'll come to the estimators later. So a Bayes estimate for data z and parameters theta is that which minimizes what we call the posterior expected loss. So we've seen what the posterior distribution is before. We've defined the loss function. But now what we're going to do is say, well, let's actually take the average over all possible parameters. And then we're going to find our the theta hat, which is our estimate, which minimizes this kind of weighted average. And this makes a lot of sense. So there are lots of appealing properties of Bayes estimates, but you can also see that we really want to minimize the loss function in regions where our posterior probability is high. Effectively, this is what this is saying. Okay, so we're going to find theta hat, which minimizes the loss function in this region of posterior probability. And another nice thing is that different loss functions lead to different estimates. So for example, if the loss function is what we call the squared error loss, then the Bayes estimate is what we call the posterior mean. And the posterior mean is, say, it's kind of, many people relate this with the best guess. Okay, so the best guess of what my true parameter is whatever the posterior mean is. Okay, because it's my, you can think of that as the best belief given the data. So unfortunately though, solving this problem is not easy. There are a few things you could do, which could be based on optimization, but more often than not, you need to sample from your posterior distribution using something like Markov chain Monte Carlo. And that sampling process could be very computationally intensive. And moreover, you need to do it for every data point z. So if you get a new z, you need to redo your optimization. Okay, and then you get a new z, you need to redo your optimization. And if we're talking about something like that satellite, which I talked about, that is extremely computationally costly. And it's actually hard to keep up. All right, so what I've done now is created a very toy problem, which explains this in a bit more detail. So this is a very simple system where I've got one data point z and one parameter estimate theta hat. And what I'm showing you the surface here is this posterior expected loss that we want to minimize for every z. Okay, so this is what the surface is. So what happens in, let's say, classical statistics, when you're doing classical inference, is that you observe one data point z. Okay, and in this case, we've got z equals 0. Right? And what we want to do is find the minimum posterior expected loss. So if we are walking along this dotted line, what we actually get is this black line here. Okay, so you know, here it is high, and here it's low, and here it's high again. So this is what gives us this curve. So traditionally, what you need to do is an optimization problem to find the minimum, and that could be using Markov chain Monte Carlo or some other method. And then we find the minimum and we say, great, that is my best estimate, I'm done. But you know, a few seconds later, another data point comes. And this time, the posterior expected loss is looking completely different because the data has changed. So you need to rerun your optimization algorithm in order to find the minimum, right? And that's going to take a lot of time again. But you run it and you find your minimum and you say, okay, theta hat is in this case 2.25. That's my best guess. Okay, let's move on. But if you look closely at this surface, actually there's this curve here, this red curve, which you can trace along the minimum, along the valley. All right? And this is very important. So for this contrived example, I actually know what this red curve is. It's theta hat equals z squared. It's simply a quadratic, right? But the important thing is there is a function here that I could follow, and and if I find what that function is, then for any z, I could tell you straight away what my estimate is without having to do any optimization. And this is really the essence of amortized point inference. So if I find that function and I extract it, okay, so now I've got a function of how theta hat behaves with z. Okay, so this function now is really useful because if I tell you z is 0, this is my data, I can tell you straight away what my estimate is. And if I tell you my z is 1.5, I can tell you straight away what my estimate is. Why? Because I've got this feed-forward function. In this case, as I said, theta hat equals z squared. So I can tell you straight away what theta hat is for everything. Now, in real applications, of course, this function is really complicated and very high dimensional as well. So this is where neural networks will come in later. But bear with me for now while we go a bit more through this. So the biggest question is, okay, let's say this function does exist, okay? How do I estimate it? So there are two options really. The first option is, which is kind of the greedy route. You can simulate a lot of data. So you simulate a lot of situations, okay, for possible simulations. So again, in the case of the satellite, I could simulate lots of CO2 fields, carbon dioxide fields, and from that run them through the forward physics model to find spectra. And then I run the inversion, the optimization, 1,000,000 times to essentially find dots along this red line. And then I can fit a curve through the line through those dots. But that entails running the optimization 1,000,000 times. So that kind of defeats the purpose. The whole point of amortized inference is that we don't want to do that, right? The second option, which actually I call the miracle of amortization, because this is what allows amortization to be possible. Use this fact. Use the fact that since this estimator, this red line that I showed you before, minimizes the posterior expected loss for each set, what it also means is that it minimizes the area under the curve, essentially, for all z. Okay. So what I'm saying is that if you had to find the area under this curve, there is no other path which has a smaller area. And why is it important that I claim this? Because ultimately we want a single objective to train our neural networks, which we'll do later. And this gives us a sufficient condition that we need to satisfy. So let me give you a picture of this. So what I'm showing you here is the red line is the optimal estimator that we are trying to find. We don't know what it is, remember, okay? I mean, in this simple example, we can just see where the valley is, right? And then follow it, but in reality, we don't know what this line is. And the green here are just other candidate estimators that I've just, invented so that we could compare. And what I'm showing you on the right-hand side here is the function value if I am walking along the red line. So you can see it's pretty high here, but then it's very white here, right? The function value is much lower. So the red line is doing this. All the other curves, sometimes they intersect the red line, as that's doing here, but they're always higher. What that means is that if I had to integrate any curve, that the integral will be smallest for the red one. In other words, if I train a neural network to minimize the expectation, an expectation is essentially an integral, of the posterior expected loss, then I will retrieve this red curve. This is why I call it the miracle of amortization, because there's no inversion involved. All you need to do is minimize this integral. And why are we choosing E of z here? So there are many integrals I could choose. I'm using E of z because, okay, now we need to go, this is the most mathematical slide, but every step is quite easy. If I choose to minimize the expectation with respect to the data distribution z, to go from equation 1 to equation 2, I'm simply writing out the definition of expectation. Okay, so if you've done some stats courses, you know that the E of x is the integral of x p of x, right? So that's exactly what I'm doing to go from this step to this step. Then I'm applying Bayes' rule. Okay, so p of theta given z, p of z is p of z given theta, p of theta. And then, to go from 3 to 4, we do what we call a Monte Carlo approximation of these integrals. So when you've got any integral, if you can simulate from these distributions, so you can simulate from p of theta, and then you simulate from p of z given theta, then an approximation to this integral is given by this sum over here. And those of you who train neural networks are probably very familiar with these sort of things, right? Because we have a loss function, and we are minimizing this empirical loss function. So these k's, these data points, the theta and z, would actually be independent draws from your simulator. So you can So of course, you'd need a lot of them, let's say tens of thousands, hundreds, thousands, whatever. But then you get this empirical risk function, you can do stochastic gradient descent, so on and so forth to minimize it. And again, it always blows my mind saying this because there's no inversion involved. I'm not even inverting once. But at the end of the day, if I train my neural network to get me this estimator by minimizing this loss function, I would actually receive an optimal Bayes estimator. All right, so I jumped the gun a bit, but where do neural networks and AI come in? So the mapping theta hat is this very unknown, very high dimensional mapping in most applications. We're going to replace it with a neural network. Okay, so there are kernels or there are bias and weights which we need to estimate. So I'm collecting all of those in this term gamma over here. And then to train this neural network, what we are going to do is essentially find those gammas that minimize this loss. Where we are simulating from our model. So literally we simulate from our prior distribution. So again, the CO2 example, we simulate carbon dioxide, and then we simulate spectra given our carbon dioxide, and we do that 1 million times. Okay, and once you do that, then you use your usual deep learning libraries to train your neural network. All right, so I wanted to go a bit through the theory to show you that we know what we're doing. I mean, there are still issues, which I'll talk about later in the red herring section, but when we train these neural networks, we are targeting a specific objective. We're not just hoping for the best that the neural network is giving us the correct answer. So you know, if we say we have an infinitely flexible neural network and things are well behaved, technically we should get to the optimal Bayes estimator, which we understand quite well in statistics. Okay. All right, so and in the end of the day, it's really simple. You're going to have your neural network after you train it, you give it your data, and you're going to get your point estimate. And these point estimates would be targets, summaries of your posterior distribution. All right, let's talk a bit about uncertainty quantification, because there is this myth, which fortunately is dying out, but maybe 10 years ago it was quite strong that you can't do uncertainty quantification with neural networks. So in this case, Bootstrap is really simple. So what's Bootstrap? Bootstrap is a way of getting confidence intervals or confidence sets associated with your estimator. And the way you can do that is you estimate your parameter theta hat, and then you simulate a lot from your fitted parameters, let's say 1,000 times, and then you fit those simulated data sets again. And that will give you a spread, and that is called a bootstrap distribution. Okay, and it's very easy to do once you've got an amortized neural network, right? Because you can get estimates in a split second once it's trained. But you can also go further and find what we call credible intervals via the posterior quantiles of your posterior distributions. Because you can play around with this loss function. There's actually a loss function, and some of you I'm sure would know that, which is called the quantile loss function. And then if you minimize that, then you actually get your posterior quantiles. And you can use that for establishing your credible intervals. Okay, so your probability that your true parameter is within this intervals. All right, so let's talk a bit now about architecture. So, okay, we want to do a neural network, but is there any type of neural network that we should be using? And this really depends on the data that you have. So if you are trying, for example, to estimate those partial differential equation parameters, like those diffusion and advection parameters, you can think of the sequence of sea surface temperature images as a small video. And you can use a convolutional neural network for that. If you have time series data, RNNs, LSTMs, CNNs. If you've got graphs, there are graph neural networks. If you have replicated data, permutation invariant networks. And this is particularly important for Bayes estimators, because we can show, or we actually prove, that when you have replicated data, so independent realizations from your underlying process, the Bayes estimators are permutation invariant. So there is a class of permutation invariant networks that you'd want to use in that case. And general unstructured data, dense neural networks tend to work quite well. So software, again, PyTorch, TensorFlow. We've been playing around with Flux recently in Julia, which is working quite well. I've just listed some packages here which can be used. So neural estimators is the package that we've developed here at Wollongong. So this is written in Julia Flux, but we also have an R interface to it, and I'll show you some soon how that can be used. But there are also some other really great packages which are not restricted to point estimation. So Baseflow, for example, I was at a workshop last week actually on this, implements posterior approximation in TensorFlow. And it's written in Python. It's written in Python, but I've managed to make it work from R. And SBI has just got a lot of nice packages, and routines that you can call, and it's mostly based on PyTorch, I believe. All right, and many of these packages are run in the same way because it's a form of simulation-based inference. Technically, if you can simulate lots of time from your underlying model, then you can construct an amortized estimator. So this is just showing what we do in our package, which is the R interface. It's written in Julia, but we have this R interface. So the first thing you need to do, of course, is establish what your architecture is. So for example, we want a convolutional neural network, so that's what you do first. And then you really need only two other things, right? You need a function which samples from your prior distribution, and then a function which simulates data conditional on those parameters. Okay? And these would be simple R functions in this case, which you pass through to the package. And then it trains, and then you can assess the estimator and see how it's doing and things like that. So generally speaking, they're actually quite easy to implement, and but I'll talk about some caveats later on. All right. So now I want to move on to an application where we analyze global sea surface temperature. So what we wanted to do here is take global sea surface temperatures from the satellite VIRS. VIRS, an instrument on board the Suomi NPP, and analyze the residuals. So we remove a quadratic trend, which kind of explains a lot of the sea surface temperature, and look at the residuals. We want to analyze how the length scales and variances of the sea surface temperature residuals are changing in space, and ideally in time as well, although we just did it for one time point. And to do this, what we did was we split the globe into 2,400 equally sized hexagonal cells, and we fit a very simple Gaussian process to it. Now, you don't need amortized estimation almost for Gaussian processes because they're actually quite easy to fit, but this allowed us to actually then compare to what you get if you don't amortize. And of course, you need to validate these things. You can't just use them without extensively validating them, so that was one of the reasons. All right, so there's a lot of what we call non-stationarity in sea surface temperature residuals, and what I mean by that is, like here, length scales in the Brazil-Malvinas confluence zone, they're very small, so things are changing rapidly, the variance is very high. But then if we look here, for example, in the southern Indian Ocean, things are relatively smooth, long length scales, low variances. There's a high degree of non-stationarity, and we want to characterize that by fitting these Gaussian process models on all these hexagons. But it's a bit of a challenge with neural networks because the data points are irregularly spaced, so they're not on a grid, for example. And also the number of data points can change massively. So we've got a few cells with a few hundred data points and a few cells with maybe 20,000 data points. Okay. So we're going to use a graph neural network which allows us to have this flexibility to construct our estimator theta hat. The nice thing about GNNs, they can be applied to these irregular spatial locations, and you can explicitly model the spatial dependence. You can set the weights on the edges to be inversely proportional to the distance between data points, and this is something which makes sense in spatial statistics. We always assume that things close together are similar, and that things further apart are not very similar. Right, so if you're not familiar with GNN, I just put this picture in to show you how it works roughly. So you'd have your spatial data points. Here I've got 4. And the first thing you're going to do is apply what looks like this complex operation. But all it's doing is doing some linear operation based on itself and its neighbors. But it's also weighting the neighbors by how far away they are from this node. And then you go and then this one, you're doing exactly the same thing. You do many convolutions, so although you have a scalar here you end up with a vector. But effectively, what you've got is what we call information propagation. So as you add more layers to the graph neural network, information starts to flow through the graph. Finally, then you're going to do what's called a readout module, and this is a stage where we collapse the graph into a set of what we call summary statistics. And this is a fixed length vector, and this is the crucial part, because it doesn't matter how many data points you have at the beginning, you're always going to end up with your same length of summary statistics, and then we're going to map those to the parameter estimates. Okay, so this is basically our Bayes estimator, which is amortized after we train it. All right. One caveat here is that the missingness pattern really matters. So if you just, when training your neural network, if we just used fixed locations or locations distributed from a uniform distribution or something like that, it actually wouldn't have worked. So generally speaking, when doing amortization, it's really important that your model matches reality as much as possible, even more than in classical methods. There's something called the distribution shift, where neural networks, where amortized estimators really start to perform poorly. And in this case, the missingness or pattern, or rather the location of the data, is part of our model. So sometimes locations are clustered, sometimes locations are more uniform, and we need to pass that information to the neural network as well. So we simulate what are called these point patterns, and we feed those into the neural network when we are training as well. Okay, so the spatial arrangements are also changing. All right, so before showing you the results, just a quick simulation study showing that this works just with 2 parameters in this case, so theta's 2-dimensional. Total training time for this is about 70 minutes on our 1 GPU. And we're also comparing to what is gold standard for estimation in this case, which is the maximum likelihood estimator. So these are some results. So what we did was we trained our GNN, and then we just threw new data at it with different spatial configurations and see how it did. And we obtained what are called the sampling distributions of the estimator. So what are these? These are, you get your data, you simulate many times with this true parameter, then you estimate and you get these box plots. Right? So if you do it 100 times, you got these box plots from 100 parameters. So that gives you the sampling distribution. And you can see that the green, which is what we get from our graph neural network estimator, is very similar to that what we get from our maximum likelihood estimator. There seems to be some bias here, but really it's not of too much concern. And actually we see the maximum likelihood estimator sometimes the algorithm goes haywire, or else the mode is a bit far off. So yeah, it's overall we see it's very comparable to the gold standard. And the metrics show that, so the root mean squared errors are very close for both of them. But this is the catch, so not the catch, this is the benefit. So the maximum likelihood estimator takes 1.2 seconds to estimate parameters from a single data set, while a neural network would require only 2 milliseconds. Okay, so it's about a 600-fold speed up. And this is, if you read papers in amortized inference, 100-fold to 1,000-fold is a typical speed up that you can get by replacing a classical method with a neural network. We also get posterior uncertainties, and we see that those are very well calibrated. So we were targeting 95% intervals, and empirically we got 94.7, 94.2% posterior coverage, which is very good. And this is what it looks like in the end. So we fitted these 2,500 Gaussian processes to on a single GPU in 3 minutes. This would take much longer if you didn't have an amortized estimator. And what do we get? We get estimates of the length scale, the variance, and the measurement error variance, and we can also get coverage probability, the interval, so the credible interval width for the 3 parameters in this case. Okay, so we didn't really interpret these. This was really just showing that we can do this. But it's for us at least, it's really remarkable that we can do all these fits in 3 minutes on a single GPU, knowing that again we are targeting in this case the posterior mean. All right, so golden ticket or red herring. So this is my experience, and other people may have different opinions, but personally I think it is a golden ticket. I think it's going to change the way we do things in the future, mostly because it enables fast inference, and frankly it even enables inference in systems that we couldn't make inference with before. So if we talk about models of spatial extremes, for example, people couldn't go beyond a few hundred data points, and with neural networks we can go way beyond that. So it's opening up new opportunities, definitely. What I like is that they are optimal in a base sense, and there's also uncertainty quantification, which can be done in various ways. What do we need to be careful of? So there's this amortization gap. So what does this mean? If you remember the first graph that I showed you, that red curve, what if we don't fit that red curve exactly? What if it is a bit off, or it's a bit skewed, right? So we think we're getting optimal estimates, but in fact we haven't fit this optimal estimator exactly. So it's very hard to diagnose in high dimensional settings especially, and it can give you a false sense of security, okay? Because the neural network will always give you, an answer, as we know, and we can easily start to over-trust it. You need many simulations. So I talked about 100,000 simulations, million simulations, and the number of simulations you need realistically grows with the dimension of the parameter space that you are considering. You need high-end computing hardware if you want to solve really complex problems. So this kind of moderate problems we've worked on so far, you can get by with a single high-end GPU, but if you want to do something really sophisticated, you'd probably need much more than that. And there is unpredictable behavior when the data doesn't come from the model you are assuming. Okay, when it comes from a different model, it's in a part of your sample space which you haven't really explored with your neural network. So there's a bit of unpredictable behavior there, which you wouldn't really get with a classical method like MCMC. You'll get a posterior distribution. It will be a nonsensical posterior distribution, but at least we kind of understand what will happen there. But with a neural network, I think all bets are off. So that is something that is being looked into a lot as we speak. All right, listen, I just scraped the surface here on amortized estimation. It's a fascinating field. Lots of people are looking at constrained posteriors, very flexible posteriors using normalizing flows. Variational posteriors, this is variational inference, and it's actually variational autoencoders use a lot of these ideas. There's a lot of work being done to tackle the amortization gap. Sequential methods, so this idea here is that you develop an amortized estimator, you see where your posterior is, and then you focus on that area, and you keep on doing this, so that you basically, it's a way to reduce the amortization gap. Ways to robustify these for out of distribution data. And by the way, we've only talked about Bayesian methods. There's a whole area on frequentist methods, for example, amortized likelihood functions. Right, so to conclude, can you fit this model 100,000 times a day, every day for the next 7 years? And now our statistician is smiling because she thinks she knows how she can do it now. And that is all. Thanks for attending, and I'll be happy to take any questions. Thank you.
Thanks very much, Andrew, for the nice talk. Yeah, I have like some questions myself. Maybe we can start while people is warming up. Well, first things first, right? You put this very nice question mark in the title, and then you ended up with a golden ticket or red herring, and you have been putting like pros and cons, right? I had, of course, like I have seen like very good points to adopt this new, let's say, amortized approach. But I had some doubts as well, right? As you have briefly noticed, maybe, and I would like you to clarify a bit on potential limitations that these approaches may have when encountering like high dimensional parameter spaces, or even going in the opposite direction, right? High dimensional parameter spaces plus very few data points to train on, right? So this also happens, right? In spatial statistics. And, I don't know. I would like to, to hear about those
Yeah.
potential caveats, or if there is some work on that, or if that can be resolved somehow, or
Yeah. So the actual size of the data set that you're going to make inference with is not the issue here, really. So once you've trained your estimator, you need to be careful that the properties of an estimator do change with the sample size. So if you think your sample size is going to be small, small sample estimators have different properties than large sample estimators. So that affects how you train your neural network. Do you want it to be a good small sample estimator? Do you want it to be a good large sample estimator? Or do you want it to be good for everything? And of course, then you need a more complex model. And we talk a bit about this in the paper. But the issue is, yeah, when you can't generate a lot of simulations, what do you do, right? Because the number of simulations is crucial. So there are various things to do here. So the first thing is, instead of working with the true likelihood, instead of working with the true model, you construct a synthetic likelihood based on your model. Now, this, in the simplest of terms, you can think of this as creating a surrogate model. So you replace your really complicated model with something much simpler, and then you design your amortized networks to instead work with the outputs from the surrogate model.
yeah.
Another thing is that you can work with summary statistics from the model. So you might have, let's say you've got this really complex simulator which generates a high dimensional object. You first get summary statistics, like the important summaries that you really want to match, and then it would be much simpler to train any estimator, not just an amortized estimator, on those summary statistics. And the JANA or YANA framework, which is part of the Baseflow group, does a bit of everything, actually. So it tries to find summary statistic, but it also develops, has two neural networks working against each other. So one of them does posterior inference, and one of them is doing likelihood approximation. So yes, I'd say, listen, it's big. It's being tackled on various fronts, but this is always going to be an issue technically. If your simulator is really hard to simulate from, you're going to have to get creative, and maybe it's very likely that amortized inference is not suitable for that application. That could well be the case.
Yep. Yes, thanks. We have a question in the chat by Simone Brazzo. He's wondering about how really effective AI systems can perform this point-wise estimation. In practical cases, they should be kind of a collaborative approach of different AI systems. Maybe that speaks to parallelization of these methods, or maybe collaborative approaches of different systems working together, or something like that. I don't know. You're not worried about that?
That's a very interesting point. Yeah. One of the things that bothers me about amortized inference generally is this equity issue, that if you want to do it for a really, really big complex model, probably there are only few institutions or organizations in the world that have the capacity or enough money to do that. And but then there's also something called Bayesian model averaging, which is kind of, you pool opinions of experts together, and we know that can create quite a good estimate. So maybe a way to get around this equity issue is to have many people with their own sorts of funding creating their own small models, and then slightly different architectures, and then if you average all of those out, use a Bayesian model averaging approach, you can actually get to something quite good. So yeah, I like this cooperation idea, and I haven't seen it done yet in an amortization context, though.
Yeah, you've been talking about this online setting, but maybe there are some opportunities for further development on this distributed computing strategy for amortizing. Maybe, I don't know. I had another curiosity more on the realm of this uncertainty quantification, that it was very, very nice, and you showed some experiments, some results on the calibration side. And I was really curious about if you, I mean, this is a hot debate, right, in the Bayesian deep learning literature. If you really need calibration, some people say that you don't really need it, you just need to be accurate, and that. Some others, they argue that no, I mean, the model has to be really well calibrated, and there are like hot debates in this literature and communities. And I don't know if you have an experience on that regard, right? On comparing this amortization with other Bayesian deep learning architectures that or models that can also provide uncertainty estimates and eventually, I don't know,
When you mean
do a kind of
calibrate,
comparison with a calibration.
so calibration, you mean the posterior, whether the posterior distributions that you get are well calibrated, for
Yes.
example.
Yeah.
Yeah, so there have been, yeah, so many of the papers that I cite in the talk actually do compare to standard Markov chain Monte Carlo. And we do as, I mean, since we're doing point estimation, we actually compare the sampling distributions of our estimators, but other papers compare the posterior distributions that they get from their amortized method with what they get from MCMC. And listen, theoretically, we know that we should be able to recover the true posterior. The question is, how much effort are we going to put into it in order to recover the true posterior? One could say that if you had unlimited resources, unlimited time, you will get there eventually. So theoretically, we know that. But even there's a lot of practical evidence that at least for, not for these super big problems, but at least for moderately sized problems like the ones I was talking about, that you do get there, that things are well calibrated, that things do match up with what you expect. And I think it's very important, by the way. I don't think your best guess is your starting point. If you want to make decisions, you need to know what your uncertainty is around that best guess. Okay, it really depends whether you say, it's this plus or minus 1 or this plus or minus 100. And that interval better be correct because it does affect your optimal decision.
Yep. I was also curious about the landscape, right? In deep learning, there is like this initiative, right, to learn about the landscape of the parameters that or the parameter landscape, the surface, that it is quite complicated, right, in most of the cases and in most of the problems and for most of the architectures, and there are like there is a lot of work trying to come up with a theory and some guarantees of reaching the local or the global minima, and I guess that this is a very nice opportunity here, no, in this amortized setting where you can actually come up with some guarantees of descent, right? But I don't know if you have, I mean, it's a whole field, of course, and there's like a
Yeah, so that's interesting. So there are, so for example, if we look at base flow,
yeah.
it's got, they model the posterior distribution as a normalizing flow, which you can treat as a neural network. And so the inference network, which I just essentially just talked about, is giving you the estimates of the normalizing flow as a function of the data.
Yeah.
So it's kind of giving you the what you need to do there in order to get your posterior mean or well, actually, or your whole posterior distribution. So this concept of I think it's called meta learning. I don't know, but there are this idea of using neural networks to train other neural networks or to find the parameters of other neural networks has been explored. It's not a field I know a lot about, but yeah, amortization can fit in there, I think, as well.
Mm-hmm. You have been showing some very nice applications on different fields, and I was really intrigued about if you're now on something completely different, or I mean you're exploring probably the application to other fields. I think that as you said, emulation or spatial modeling or spatial specialization, there are very nice and urgent exercises that we are doing, and I don't know if you're into something else, right? Right.
So regarding, are you talking about regarding amortized
Yes,
estimation or?
yes, yes, because I
Yeah,
see a lot of opportunities, for example, for you can plug in whatever neural network, right? And it probably, capturing spatial and temporal dependencies is uh,
yeah,
a big field, right?
yeah.
Yeah.
Yeah. Listen, it's a really big field. So currently, for example, with we've submitted a paper. It's under review, where we developed amortized estimators for the case where we have censored data. So, for example, data is censored for whatever reason. Actually, censored data gives you some information about the process. The fact that it was censored, for example, it was too high or too low, that actually gives you some information. And we are using that to in the context of atmospheric pollution. So, I mean, it's a bit complicated as to why we're doing that, but yes, so for example, estimating spatial extrema of air pollution, we use something known as the censored likelihood, and we're using neural networks there. We're starting to look at neural networks for analyzing, for example, the nature of fire extremes. So in Australia, we have a lot of bushfires, and we want to forecast, what for example, the extents of bushfires will be and things like that. And again, that's a lot of modeling in there with parameters, and we're looking a bit at that. The thing I talked about, the orbiting carbon observatory, NASA satellite, actually that work hasn't been done yet. I mean, we're still looking at it. So yeah, listen, the amount of applications is immense where this can be used to good effect. And of course, there's a lot of validation which needs to go into it to make sure, before something becomes operational, we need to be a lot of validation. But I see a lot of potential here. Yeah.
Thanks very much, Andrew. It was very nice to have you here. It was a great discussion, and also around a very timely topic, actually, both in the machine learning side and also in the geosciences. So thanks very much for presenting, for taking the questions, the time. Now I think it's time for closing the session. Also, I would like to thank the attendees. Thanks for staying with us today. And remember that you can still continue conversations in the neural network area if you're registered. That's actually a good opportunity to follow up with some of the remaining questions that are there in the chat, or you wanted to ask Andrew. We hope to see you in our next talk, in our next seminar series of AI for Earth and Sustainable Science. Thanks, everyone, and have a good day.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.